We need to be very, very quick in this. If I ask questions, please try to answer if you know it. Don't keep it trying to validate your answer if somebody answers. Yeah, it helps yourselves and others as well. Now, consider regression model yi beta 0 plus beta 1 xi, usual setting, and also suppose that this model, population model, satisfies A1, which says expected value of ui given xi is 0. A2 says xi and yi's are IID draws from their joint distributions, and A3 says what does it say? Force moments. Yeah, they have finite non-zero force moments. That's what it is basically in mathematical terms, but we need to discuss what they are in turn, yeah, in one by one. So the first one, A1, what does it imply?
Conditional distribution of error term and x is like 0.
Conditional mean of error term is 0, right? And also ui is independent of xi, yeah? Yeah? Independent assumption here, yeah? Independence assumption. And how about xi and yi? A2 being IIDs. They are independently randomly drawn, yeah? Yep. And how about A3? Basically, A2 means, sorry, identical means, yeah? A2 means identical means. This is assumption. In your data, it might be the case, yeah? Okay, A3.
It has infinite form.
Finite, you mean? Because it's less than, not equal. It doesn't have the less than and equal. It just has less than infinite. So, in economics, what does it mean having a finite force moment? Not much fat tails, yeah? So we don't have outliers in the data, yeah? OLS assumes that your data doesn't have outliers according to this assumption. This is an assumption. You might have an outlier, or 2 or 3. What happens to OLS estimator or the gradient, estimated gradient, if there is an outlier? In the data, if you do not delete it from the data. No. Let's say you collected some, you're looking at the income and some variables, and majority is there, and some guy earns a few million here. And if you fit as OLS, you get something like this, yeah, fitted Y. The gradient here, which is the beta hat, is biased upwards, right? Because of these guys. These are, it appears these may be outliers. I mean, not necessarily outliers. Let's say there aren't many of them. There are few of them. Not many. They are pulling this thing up, yeah? So beta hat will be biased estimator. Now, we would like to have none of these outliers, because that's what the OLS assumes. When you fit the OLS line, you get this, which is much more like a better fit, isn't it? You have a high R squared, low SER, and significant F, if this is the case. But if that is the case, you have the opposite of all. So if that assumption is violated, A3 you'll have a biased, yeah, beta 1. So the gradient is obviously now lower here, right, than the one we would have drawn if there is an outlier here. These outliers are included. So as A3 assumes that there's a finite force moment, the fat tails are shorter. The tails are shorter of the distribution of each variable, right? Not long, not with the outliers on the extreme cases. Okay, we know this now. Intuition is there. Next. I am emphasizing this in more details because you know what? Next week is your exam. But I don't know where. But assumptions are usually embedded into question and something like this. Question. Yeah, some questions like this. So you should understand the assumption to solve these questions. But I don't know what's in the exam because she won't. I mean, lecture is obviously independent, so you won't. We won't know. And I know what you know in the forum, the module forum. What is in the module forum is important, so you read it, and also you will receive email stating which rooms you will be in. Apparently there are 3 rooms, 3 groups. So make sure you read this and don't be in the wrong group, wrong room, because you won't be given an exam test. I think exam paper. That's what I heard. Okay. Suppose that now. So let's read further. It's just we are still reading the question. Suppose that yi is measured with error, so that we have y tilde I being equal to yi plus wi. Now, this is the actual true yi, the true values. But then we measured this with wi. So can you give an example, a real life example of incorrectly measured variables that could be more frequent? I think your slides have them, or maybe in the book. Income usually is incorrectly measured. That could be dependent variable in many cases. Tax payments, yeah, people individually try to show that they paid high taxes, yeah. So in fact they may not be, so they put add a positive error, while income will be negative error here if y is income. So yeah, so we have some sort of measurement error in our y. So y is the dependent variable here. However, what we know is that wi is iid, and it has the expected value 0, and its force moment is less than infinite. Now consider this population regression. Now because we measured incorrectly, and we will be using this for estimation of betas. So consider this measured variable model where this is vi is the regression error using the mismeasured dependent variable yi tilde. A, show that vi is equal to ui, so show vi is equal to ui plus wi. In other words, this vi is a composite error consisting of this sum of this. Now I need space, so I'll start new. Erase. Show that the composite error is this in this model. Now what we know is that the measured error, a mismeasured variable is evolving according to this formula. And we also know that population model is, when it's not prone to errors, or is not doesn't have the mismeasured yi, is this formula, right? We'll use this too to prove this, to show that the composite error consists of error from the original regression and error from measurements. Now using this, solve for yi. plug that into this, you will get and from there it follows that ui tilde yi tilde is actually some ui plus wi. And remember what we have? It's vi. We just showed that vi is actually sum of the two errors. Now now we know that the vi is a composite error, an error term for this model. Also, we also know that this model, the original model here, satisfies three assumptions according to the question. Yeah, if you read, it satisfies three assumptions. Now the question is, does this model with the mismeasured yi satisfy the three assumptions we have? OLS assumptions. Does this satisfy this assumption? First assumption. We need to prove that. We need to show that if that is the case or not. So if you read the question, assume that wi is independent of yj and xj for all values of I and j, has mean 0 and has a finite fourth moment. So we assume that wi as mean 0. I'll write it later. Oops. And also it is also independent of xj and yj, and also fourth moment is non-zero finite. In that case, all we need to prove is this. Does this hold? Because it's the error, isn't it? It's the error. Can we prove that, given what we've just seen? Yes, we should be able to, isn't it? Yeah, shouldn't we? Sorry, just substitute this into vi, because that's what vi is equal to, isn't it? I mean this thing here. What is this equal to?
0.
It's 0, yeah? It's given that it's 0. How about this? If it's independent of xi and if it has a mean 0, must be 0. So we just proved this. Okay, we go to A2 now. Time is running fast forward, so erase. Can I erase it? How about assumption 2? Assumption 2 says these should be IID random draws. Are they? We know xi is, yeah, individually it is, but we don't know if this is. But what we know is that yi tilde is basically yi plus wi. And from given details, this is IID. This is IID, right? Then sum of the IIDs is also IID. You just need to write this in essay, yes? Done. A2. A3. I'll be quick now because of timings. I should have run earlier. So yi hat tilde, again, we'll repeat the same thing here just to know where we are now. The assumption, third assumption states that this should hold. This should hold. Does it? It should. Let's see. Let's check that. We know this holds because it's given already in the question. If you read it, it has a finite force moment. Also, it's stated in the question B, it has a finite force moment. Sum of the two variables with finite force moments gives you a finite force moment third variable. And it's like you sum element by element two variables without outliers. You end up getting the third variable without outlier, right? It doesn't create. If you sum a variable with an outlier and a variable without outlier, you will have outlier variable with a variable with an outlier eventually. But then when you have finite force moments in each variables, then they should give you a third variable which also has a finite force moment. So given that, we just proved all this. Yes, yeah. So xi and y tilde I have finite force moments. In that case, it's a big implication here, guys. This is the underlying thing. The main thing here so far we've been doing is whether so I'm writing it here, whether we can estimate the betas here consistently. So this would be consistent estimated and unbiased, isn't it?
Oh, no, because we don't have a sample size.
So this is B. No, it's a population, so it's everyone in there. It's not sample. It's a population regression, and we just take a large sample. Assumption is a large sample from the population. So if you take a sample of 4,000 or 5,000 observations from this population, it should be fine, yeah. And OLS expects the population size, sample size to be more than 100. That's another assumption there, but we usually violate this key one. Sample size will be usually 30, 40, yeah, it's a small sample size, yeah. So we just answered question C as well. OLS estimator is consistent. Estimators here, because beta 0 is being estimated as well. Because when do we have the case of not consistent estimators and biased estimators? So in other words, usually the outcome of this is, the implication is that none of these two is correlated with X. That's why you have your beta 1 can be estimated consistently. None of the two. I'll give you, for a different perspective, another example. It's a digression from what we're doing, but I think it highlights what we just did. Imagine our X is mismeasured. When the population regression is. You don't have to copy this, just to highlight what we've just done. Now, If that's the case, plug this into this. Sorry, it would be better if I just rewrite this. If I just rewrite this. And call this VI. What's wrong with this regression model? If you understand what's wrong here, you certainly understood the one with the YI. And then you'll be able to do the exam very well. Performing the exam. Well. I'm not claiming that there will be something like this in exam, but it's just assumptions are key here. Yes, what's wrong with this example? Or something is wrong with this estimation here. The OLS estimator is not valid.
Errors are correlated with
Which one?
the error is related with X1 tilde.
This one.
No, V.
This one. Yeah, because this contains WI, isn't it? Which is actually, XI is a function of WI. So, these two are correlated. You have omitted variable bias here. A case of, but it's actually the mismeasurement error bias. Errors in variable bias. This is called errors in variable bias. Now, do you see the clear difference between them? When error y, which is the dependent variable, is measured with error, no problem with it, isn't it? Not a serious problem. We just proved it earlier. But when x is measured with error, it's a big problem, right? We're violating this assumption. It's not equal to 0. In other words, there's correlation there. Okay, next. C is answered. D, yes, if it's consistent estimator, we can construct the 95%, 99%, 90%, or any other confidence intervals, and they are valid. And they can be constructed in the usual way. E is implicitly answered already. If you want to discuss this, you're welcome to do. E says basically measurement error in X is a problem, but when the measurement errors in Y is present, then this is not a problem. And we just showed it mathematically and discussed it, yeah, quickly.
This is also because one variable is dependent, the other is independent.
Because it depends on the position where they are. Role of it. Is it dependent variable or independent? If the error is in the dependent variable, which is Y, it's not a serious problem, but there's a problem with it though. One problem. There's one problem. Remember this case, that's what we had. The error was sum of the two errors, right? And none of these two correlated with xi. So we have an unbiased consistent estimator. But take the variance operator. So on both sides. Var expand this basically. what is this variance of ui is equal to? We usually leave it as it is, or sigma usually, yeah? You can leave it in the test or not. Now, how about this?
If it's independent, 0.
And we know they are independent, isn't it? Yeah, from the equation, so that's 0. And this is basically just simple variance of that. Notice that the variance of the errors in the second equation, the one with the measurement error, is larger. And this actually usually leads to large standard errors in betas. And that's the problem with efficiency, isn't it? OLS is not efficient. But that's not a serious problem in this case. The serious problem is consistency and biasness. And I showed you graphically how the beta would be, by how much the beta would be biased if you have outliers. And if your variables are not independent of x's, yeah? And if they are not random. Any questions? Okay. Now we go skip 3, 4. That's because these are discussion questions and you will be able to do this. You will get the answers for this. Time series, we haven't done any of them, so we have to do this, and this will be in your test apparently. Time series questions. And in class 6, we skip question 1 as well because it's not time series. You just have to do some microeconometric exercise. Exercise. That's equate demand and supply equations and get the solution for the first question, and the rest is just a standard. But I will upload the video for this. So I want to do some time series analysis or questions with you to explain you what stationarity and non-stationarity is, and when you have these terms in your test, what to deal with them, how to sort of manipulate them, yeah, variables. So let's start class 6, question 2. Suppose that YT follows this moving average or the one moving average, MA1. Actually, this is always T now, not I. Guys, when it's time series, subscript is always T, not I. And we know from given details, 0 is some constant. Notice again, this is not dependent on T. Sigma u squared is a constant value. And before we go and solve this, I would like to ask you the difference between stationary and non-stationary time series. Can you give examples for both of these? Notice that we now have x-axis time. There's no x, no y. This will be y now. Any examples now I could draw here? Yeah, what's that? Give an example.
Constant mean, constant variance.
Yes, give an example of such process. Economics, macro variables. Which of the variables have constant mean and constant variance usually? What variables do you think exhibit these features that we can call stationary variables? Does GDP have stationary mean? Constant mean? Or constant variance over time? you have in the slides that it looks like this, yeah? And in your slides, you have an example of stationary one as well. Constant mean and variance. What is it? How about inflation rate?
It's not constant. I mean, it does depend upon your expectation.
No, historical series, historical. Is it, if you take the times, the historical time series of inflation rate, is it constant? Growth rates of GDP is constant. So let's say inflation rate is expected to go. I mean, it doesn't have to be inflation rate, but yeah, something like this, yeah? It doesn't have to be like very white noise, very much white noise. Now, with time series, when you have constant mean, constant variance, actually this is, I used to do this in red, so let's do it in black. The variance will not exceed this sort of band. You see it, this band is the sort of variance band, yeah? The series do not fluctuate away from this. I mean, across the line above and below far too long. Doesn't stay far too long away from this line as well. So it goes back within this band. So that's as a variance. In the long run, it has a constant variance. And at the same time, constant mean. Notice that the series always goes up and down of this line, above and below this line, but will always come back to this on average, yeah? It's always snaking around it. So on average, it will also have a constant mean 0, let's say. It doesn't have to be inflation rate, but average. Inflation rate, I think, is on average is 2% in the UK usually, isn't it? In the last few decades. Now, let's take chunks. I assume these are in equal intervals. In this interval, we can see there's a constant mean. If you just sum up and divide by the number of years, you get the constant mean 0. The same here, constant mean 0, constant mean 0, constant. But the mean of GDP is this value here, somewhere here. Somewhere here is GDP mean. For this, it's somewhere there. And for this is some. So over time, mean of GDP is increasing. It's not constant. If you see it from this perspective, right?
So inflation rate or growth rate?
But this one is going, yeah.
Inflation growth rate or just inflation rate?
It's inflation rate, which is the growth rate of CPI inflation, let's say. Price levels. This variable could be MA or any other variable with constant, U 0, average value 0, and some constant value. But the variance here is also changing. So in this period, for example, variance is low. In this period, could be high, and so on and so forth. Now, is this clear, the difference between these two series and processes? Okay. It really helps with the chunks in the next solution part. So let's clear this. And let's start question 2A. Now we have to compute the mean and variance of YT. So take the expectations on both sides. What is this equal to? 0 minus theta. What's this equal to? Also 0. I just show you with chunks. On average, it's 0, isn't it? Yeah. Whether you lag by 1 year or 2 or 3 years, the stationary variable will always have the same mean. And then in this case, if This is 0, then this should be 0 as well then, isn't it? So 0. And variance, take variance on both sides. You need to sort of understand that this is the case. Doesn't have to be the same exercise in the test, but similar exercise imply the same. I mean, the same rules apply for stationary values. There's ut minus 1, and I should put here theta squared. Sorry guys. Theta squared times variance ut minus 1, this one. Theta squared times variance ut minus 1. You know what this is, yeah? From exercise details. How about this?
Are independent.
They are independent, yeah? Yep. This ut, variance of ut minus 1, is it 0 or something else? Just example, just did you draw the line? I just showed you with chunks. The variance was the same all over the place, yeah? It's the same thing, guys. Constant variance. Time series. T minus 1, T minus 2, variance of T minus 10 is also equal to variance of T minus, UT. So what I mean is this.
I don't know.
If it's stationary,
Yeah, I don't know if it's stationary.
it says constant variance. Sigma u squared. No T. No T. No T subscript. It's given in your question, guys.
It's Greek, don't be surprised.
So, you see, if the sigma is does have a T subscript, variance is changing over time. In other words, if you think of this, as T, the variance is changing. It just goes, this volatile sort of process. It's not constant. It doesn't stay constant all the time. However, in this example, we told that this T doesn't exist there. It's not there basically. So T minus 10, fine, it's sigma u squared if it's stationary variable. If it's MA, moving averages. Yeah. Okay. Next, compute the first two autocovariances. Time. Do you know if there is a difference between covariance and autocovariance? Anyone? More often students get confused by the terminology, although this means the same thing as this. It's the same thing. It's just in case of time series, it's autocovariance, not covariance. So the same rules for covariance operators apply here as well. So we'll use the covariance operator to compute the autocovariance for this variable. So I'll try to be quick now because of timing. Essentially, if you just plug in the data generating process, which is ut minus theta ut minus 1, comma, ut minus 1 is generated by ut minus 1 minus theta ut minus 2. So we shifted it by a lag, time lag. And now, this is comma, guys. This is comma. So t minus 1, comma, ut minus 1, theta ut minus 2. Now, can you expand this bracket using the covariance operator easily? Are you all familiar with this? Yeah? No? No? Okay. So this would be covariance of this ut with ut minus 1. Then the ut with this ut. So this would be this minus here and theta. So minus theta covariance ut and ut minus 2. Notice that theta is a constant, doesn't have t subscript. It's not that, so operator covariance operator doesn't apply in this case, or cannot be used in this case too, in the same way as the random variables. Next, now this term with this, so minus, this is minus here, covariance of theta ut. Sorry, this theta comes out again of the operator, so this would be, then I'll have to rewrite it anyway again. So it's this with this, and minus theta and minus theta ut minus 1. This gives us plus theta's out of the bracket times theta. You'll have covariance to ut minus 1 and ut minus 2 equal. And now we need to figure out what this is mean. This is it. So covariance between ut and ut minus 1 is yes, 0, thank you, minus independent, any lag, yeah, it's first lag, second lag, doesn't correlate with ut, minus this, 0,
It's 1. It's the same, isn't it?
it's the same thing,
So it's 1.
it should be variance then, isn't it? Variance, yeah, good. So theta variance ut.
So why is it 0 again?
This,
Yeah.
they are independent of each other. The realization of ut is,
Because different time.
yeah, at different times. This is at time t, this is t minus 2 in the past. So they are independently realized, or they occur independent of each other. And how about this? T minus 1 and t minus 2. 0. Using the same principle, we'll do the second covariance. So I don't have to explain here, I guess, because we've done the first one. So I will just quickly do this, guys, because of time, and we go to autocorrelation next. I just realized that the users are becoming subscripts on their own. Sorry, this is actually that, and here this t minus, what's this? 3. And expand the bracket as usual, covariance between ut and ut minus 2 minus covariance between theta ut minus 1 ut minus 2, the minus covariance between so this is 0, this is certainly 0, certainly 0. So we'll have 0. If all of them are 0, obviously, yep. ut and ut minus 1 independent.
Because first time the covariance was different.
Because it says first autocovariance is with 1 lag. Second autocovariance is 2 lags, so this is the, yeah. Third autocovariance will have the t minus 3. 10th autocovariance will have the t minus 10. Yeah, good question. Hey, some people are, oh, it's time, sorry, autocorrelations will be on the video now. Will you please return the attendance register and, yeah. The interesting thing is, yesterday I spoke to a student who says the videos are boring.
Какой пиздец, это мрак. Что я за хуйню учу?
Being recorded. Nice. Let's look at